Hello, welcome to Maths with EJD. In this video, I'll be talking about minimum spanning tree using the Prim's algorithm. Of course, I have this already, something like this, not this exact question, as part of my playlist on linear programming. So, but I mean, I felt I should just do this also to add more to that idea. So the minimum spanning tree of the network. Now this is going to be under the fast math solution playlist. Um, so here, of course, first of all, the idea of minimum spanning tree is that imagine we have 9 cities as presented, cities A to I. So we want to make sure we imagine you want to make a road connection such that at least every city is reached by a road. I mean, without unnecessary networks, without making sure that there are no closed loops that you now begin to run in a cycle, right? That's the basic idea of a minimum spanning tree. Every city has to be reached, but then you don't want to waste effort, reaching a city that had already been reached. So that's the idea of minimum spanning tree. And there are two methods of approaching this. That's the Prim's algorithm and the Kruskal's algorithm, which I'm going to do. Same problem. I'll use Kruskal's algorithm in the next one. Now, for Prim's algorithm, what you basically do is you start from the beginning, which is A in this case, and then you move based on the distance, the possible distances you can go. Then you select the smallest of the distances, and then you keep moving like that. Then you also have to guarantee that there are no cycles. A cycle means that you don't have like you don't have A, B, E, for instance, where all the three of them are connected in a way, or you don't have A, B, C, D, E, where you can have them, just running within the loop. So you don't want to have that, but you want every city reached. So let's go ahead and do the Prim's algorithm. So for Prim's algorithm, right, this is how you go. So um you are starting out from A, right? So you can go from A to B and you can go from A to E. Those are the two possibilities. But the Prim's algorithm says choose the shorter distance. So and the shorter distance here is just A to E. That's 42 kilometers. Okay. Now, the next the next thing is don't forget every place has to be reached, but it has to be done in a very strategic way. You want to choose only the short distance. Now, A and E are in the minimum spanning tree, right? A and E are in the minimum spanning tree. So from A or E, you can now check the next short distance. So you see, you can go from okay, maybe I should also do this. You could have gone from A to B, you could go from A to E. All right. So now the next movement can actually be from E to G. You can move from E to G, you can move from E to D, you can move from E to B. Okay. Then of course, so only now you can move from A to so A to B is still in contention, right? So you can still check that out. So of everything where we have arrow now, which one is the shortest of them all? So you have A to B, which is 45, which we had done before now, but it has not been reached yet. You have E to B, 85 kilometers, E to D, 47, E to G, 41. Obviously, 41 is the smallest of all the possible values there. So it means that the next connection you're going to make will be from E to G. So you are going to say like construct a road from E to G, or maybe you are doing internet connection. So you just want every city to have a mast. So now G has entered. So next thing is from G now, which possible places can you reach? I mean, from not even G alone. Now A and AEG are in the connection. They are in the loop. Should I say, I think loop is not the word. They are in the minimum spanning tree. So which possible places can you reach again from A, E, G? Okay. So what we already have the one for A sorted. You can reach A from A, we can reach B and E. So, but already A and E, AE are already in the loop, but B is not there yet. But then what are the possibilities again? So from G, you can reach H. From G, you can reach D. From G, you can reach F. Okay. Where else can you reach? I think those are the only possibilities as far as G is concerned. So yes. So of all these places now, I mean of everywhere, including where the beginning A to B, and everything everywhere that has not been reached now. So of everywhere that has not been reached, which is the smallest of them now? So you have A to B 45, you have um D to G 58, G to H 52, and you have G to F 20. So obviously 20 is the smallest, so you go G to F now. So G to F is the smallest of these things you have now. So the next thing is now A, E, G, F are in the minimum spanning tree. Okay? A, E, G, F are in the minimum spanning tree. So again, you have to check where else can you reach from everywhere you have reached already. Okay? So from F, of course, you can reach C from F like this. Then from F, you can reach I. From F, you can reach H. Okay? Where else can we reach? Yeah, these are the possibilities. So of all this now, which is the smallest? So here you have 25, you have 52, and you have 31. Obviously, 25 is the smallest, so you just reach 25 from C. So far, um, so far, A, so we have reached A, E, G, F, C, right? So from F now, where else can you go? I guess I want to switch over. I want to switch up this. Let me change to, let's say, blue. So from F now, I mean, from C, you can reach 45. Okay. From C, you can reach D, which is 48, because B and D have still not been reached, right? So from C, yeah. So of everywhere that have not been reached, so you see B has not been reached, C has not been reached, D has not been reached. Then I and H have also not been reached. So of all this now, which is the smallest? So obviously, you see that the smallest of all those again would have to be um would have to be H. Okay. So we have to move from F to H now. We have F to H. F to H. Now, so from H so the only thing we have now is from H, you can only move to I. Every other one has been considered. So from H, H has been reached, I hasn't been reached. So if you look all over the place now, you see 19 is small, is the smallest of every other possibility. There's 45, there is 19. H, now in the MS we have AEGF, we have AEGF, um, AGF, CH are all in the loop. Or let me say AE, ACE, FGH. So, but the smallest again is still H2I, which is 20. I mean, which is 19. So you can reach. So now I has been reached, but then we still have B and D that have not been reached. So if you look at, so now there's no, so you just have to look around because almost everything has been covered except that B and D have not been reached because every city, so the idea of minimum spanning tree is you have to reach every city, making sure that there's no closed loop. Okay. A closed loop is something like, okay, I've demonstrated that before. So now if you look at, if you look at A, B, and D have not been reached. So if you look at all the values remaining now, so you'll discover that we can connect. Okay, from everywhere that has been reached, sorry, it has to be from everywhere that has been reached. Where else can we reach? So you see, we can reach from A to B because so if you look at, okay, we can reach from C. Normally, there's 40, right? But we cannot connect something that is not already in the MST with anything. So B and D cannot be connected together because none of them is in the loop already. So I think it's pretty easy. So we can either connect A and B or C and B. But let me go. So since you started from A, so let's just connect A and B. But now D is yet to be reached. Okay, D is yet to be reached. And since D is yet to be reached now, the obvious choice we have to make now is to connect B and D. and that would be the minimum spanning tree. Now, minimum spanning tree is different from shortest route because the idea of shortest route is you don't have to go through every city. You just need to know the route, the shortest route that will take you from A to I, even if it means going straight from A to I or just passing through 2 or 3 cities. But in the case of minimum spanning tree, you have to touch every city with as minimum number of linkages as possible without having a closed loop. So, imagine if I move from D to G, now that the A, B, D, G, E will be a closed loop. So that'll be wrong. So, but now we have reached A, B, C, D, F, G. We have reached everywhere in short. We have reached A, B, C, D, E, F, G, H, I without having a closed loop. A closed loop will be anything like maybe something like this or something like this or whatever, however the shape is, even if it is a pentagon, you know, that we totally want to avoid such closed loops. So, but from what you have done now, we don't have any such closed loop, and every city has been reached. So we are looking for the minimum spanning tree, right? So, um, so I can just say, okay, let me remove all this to avoid confusion. So we now have the minimum spanning tree consisting 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 of um consisting of vertices A, B, all the vertices A, B, C, D, E, F, G, H, I, and edges now. So the edges will help us get the distance. And edges, so we have AB, which is AB is 45 kilometers. Okay. We have AE. AE is 42 kilometers. Okay. AE is 42 kilometers. Then we have BD. BD is 40 kilometers. I'm going alphabetically. So BD is 40 kilometers. Then we also have, what else? We have EG. Okay. EG is 41 kilometers. EG is 41 kilometers. Then next we have F, we have CF. Okay. We have normally CF should, okay, let me be perfectionistic and go CF first. So we have CF. CF is actually 25 kilometers. This CF is 25 kilometers. Then now we can go back to EG. EG is 41 kilometers. EG is 41 kilometers. Then after EG, we have FG, right? FG is 20, FH is 31. So FG is 20 kilometers. FH is 31 kilometers. And lastly, we have HI. Okay. We have HI, which is 19 kilometers. HI, and that is 19 kilometers. All right. So we need that total distance. So it means that if you want to maybe make road networks in such a way that so that every city is reached, without on any closed loop. Of course, maybe it's better for a telecommunications project because of course it's not a bad idea that all the possible roads are reached. But here, imagine internet. We just need a mast in each city. So I want to follow the shortest. Maybe you want to lay cables to get the masts there or something like that, or fiber optics. So maybe in that case now we can now. So maybe it's a better idea in the case of telecommunication. So the total distance, if you compute all that, will just be okay, this is 97. If you add that to 40, that is 137. If you add that to 25, that is 162. If you add that to 41, that is 203, I think. Yeah. 203. Yeah. 203 plus 20, that's 223. 223 plus 31 That is 223. Is that correct? 203, 223 plus 20 is 160 plus 41 is 3. Yeah, 203. 223 plus 31 is 2254, I believe. 254. Yeah, 254. 254 plus 19. That will be 2. Is it 273? Okay. So AB is 45, AE is 42, BD is 40, CF is 25, EG is 41, FG is 20, FH is 31, and this is 19. So this is, oh, okay. I made a mistake from the very beginning. I was wondering. So yeah. So 42 plus 47 is 4 plus 45 plus 42 rather is 87. 87 plus 40 is 127. Okay. 127 plus 25 is 152. 152 plus 41 is 193. 193 plus 20 is that's 3 2. 190 plus 20 normally is 210. That's 213, I believe. So that's 0, 1, 2. Okay. Yeah. 210. So 210 plus 31 is 241. So 241 plus 19. No, that shouldn't be. Uh, okay. 193 plus 20 is 3. So 213, yes. So 213 plus 31 is 244. Finally, 244 plus 19 is 263. So the total distance is 263 kilometers. So you need to lay cables for 263 kilometers for the minimum spanning tree. And that's how that goes for the Prim's algorithm. So in the next video, I'll be doing the same problem for Husserl's algorithm. So if you have not subscribed to this channel, be sure to do that right away. Hit the notification bell so you can always get notified each time a new video is released. Comment. Let me know if you want to solve a problem or teach a topic. And then like and share so that more people can have access to this great content. Till then, bye.